Okay, so I'm tremendously disappointed that I'm not in Munich right now because I was very much looking forward to the opportunity to interact with this community. I'm going to carry on anyway and tell you, give you a little flavor of some of the activities going on studying many-body physics in Moiré materials. So Moiré materials, as I'll emphasize again in just a moment, are some kind of artificial periodic system, maybe partly analogous to the artificial periodic systems that you can make with cold atoms. They have bands and they have interactions, and you can tune the bandwidth in particular, and therefore tune the importance of interactions in the system, and in this way explore the strongly correlated electron problem. The way the Moiré periodicity works is, first of all, it works much better than anyone ever could have hoped. Thanks to very clever experimentalists making things happen. And it is based on two-dimensional crystals, a topic that grew out of graphene and has continued to develop over the years. I'm showing you here on this slide two-dimensional crystals, a blue one and a red one, twisted relative to each other by 5 degrees. And as you can see in this illustration, when you have two 2D crystals and they either have different lattice constants or they're twisted, by small amounts, the stacking arrangement, the atomic scale stacking arrangement between the two layers varies slowly on a lattice scale and periodically in space. And that's the periodicity of the Moiré pattern. So you can make artificial periodic systems, and you can work on an energy scale where the atomic scale incommensurability of these structures doesn't have any observable effect. As Matthias said, thanks to incredible experimental progress, there's been a lot of interest in what's been observed in these Moiré materials. And so part of the interest, or maybe the larger interest in this, is that you can study physics that occurs in real crystals, and you can study it better for reasons that I will explain, much like people hope to do with cold atoms. But I'll also emphasize that some of the many-bodied problems that arise in these Moiré systems, particularly in twisted bilayer graphene, are quite distinct from what usually arises in a metal, and they could be simulated with cold atoms. As I'll say, I'm going to give you run down a few examples of different kinds of effective, of many-body models that you can make with this Moiré construction idea. And but one thing I want to emphasize at the beginning, which reminds me very sadly, given our current situation, of my vacation in Priano last summer. My wife would send me out every evening to get some wine so we could talk about what we'd done during the day. And I became friends with this guy right in front here, you see that with totally white hair, who's the proprietor of the shop, is looking over all the action. And so we became quite friendly because he saw me every day. And he eventually told me that he'd been running this shop for 35 years. And he explained to me the title of his shop was Everything for Everyone. But he said that he'd come to feel very badly about it because he knew it wasn't true. And I can say from the wine selection, it certainly wasn't true. And the same is true with these Moiré materials. We can do lots, but it's not a really flexible way of making artificial two-dimensional interacting particle systems. But it does have a lot of advantages, some of which I list here. Among all the ways we have for trying to make periodic systems in solid-state materials that have a superatomic type periodicity, this works better than any other, works better than any lithographic technique or any kind of chemical patterning technique, much better. It has very conveniently tunable parameters that control the strength of interaction, the bandwidth to interaction strength, let's say, just by twist angle, and I'll be giving two quite different examples of that. Another thing that's very important is that you can change the number of electrons per period in these artificial crystals simply with electrical gates. And this works just marvelously well because it turns out that in typical systems, the unit cell area of these Moiré crystals is around 10 to the minus 12 square centimeters, which is conveniently large compared to atomic scale. So that means that you can pull enough electrons in and out of these 2D systems using gates to fill up the bands. But it's also not too large. If the periodicity was too large, it would be practically impossible not to have the physics dominated by accidental disorders. So it seems to be just in a very fortunate range. So I'm going to talk a little bit about how you make, how you understand at least these Moiré systems and in a simple way. And I'm going to talk about mainly about two classes of phenomena, if you like. One is that have been observed in these Moiré crystals so far. And the three things that are listed there have been observed is Chern insulator states have been observed. If anyone doesn't know what a Chern insulator is, I'll be saying later. But these Chern insulators are different from the ones that have been seen previously, and I refer to them as orbital magnets. So I'm going to talk about orbital magnetism and some of its unusual properties, which is, I think, becoming quite well understood. And I'm also going to talk a little bit, if I have time, about superconductivity, and which is not well understood. So let me start. Okay, so this is the simplest example of a Moiré system. It's based on a two-dimensional crystal, a transition metal dichalcogenide single layer system. So the bands are a function of two-dimensional momentum. This system has a triangular Bravais lattice, so its momentum space is that of a triangular lattice. And I'm going to be talking mainly here about density tunes so that the states we're interested in are near the top of the valence band. I hope you can see my cursor. And the main thing I want to point out is that near this momentum, and the Moiré patterns are smooth, so where we are in momentum space, whether we're near this point or near this point, is a quantum number of the system, which we refer to as valley. So states in a given valley at a given maximum of the Brouin zone, turns out in this system are spin orbit split. So that means there's only one spin for every momentum. And in the perfect crystal, before we start to make the Moiré modulation, and basically the complexity of the effective Moiré Hamiltonian is determined by the number of bands you start with. And in this case, there's just one state at each momentum in the energy range that we're interested in. These two states, yeah, okay, I'll go on. So the two states that were kind of close together there are split by a spin-orbit coupling energy, which is about 0.4 volts and big for our purposes. So here's a simple picture to understand the effective Hamiltonians of these systems. It's based on a kind of envelope function or effective mass approximation commonly used in semiconductors, which is based on the fact that all of the states you're interested in are localized in are near a particular momentum, or in the general case, maybe a couple of momentum that we distinguish by valley. And so what I'm going to talk about only applies when all of the states in the energy range of interest are near one momentum of the one or several momentum of the underlying crystal. And that means this only applies for semiconductors or semi-metals in the jargon of the field. And what happens in semiconductor and semi-metals is if I view the Hamiltonian of this crystal, for example, the red crystal, as a function of as I move the crystal underneath, so the moving the crystal underneath is characterized by a stacking vector called D here. And if I move that stacking vector by a lattice constant, obviously the stacking hasn't changed. So, and in the Moiré pattern, basically the stacking is changing, but it's changing very slowly. So, so this Hamiltonian is periodic in the Moiré pattern, but with the periodicity of the Moiré pattern and not some atomic periodicity. And since we only need one momentum, we don't have to worry about uncertainty principles, since this length scale is long and we're interested in a certain range of energy. And so basically I can add to the Hamiltonian to account for modulation, a term that is dependent on position. And in the case here where I only have one state with a certain momentum, then that quantity, which has the Moiré periodicity, is just shifting the energies of those states up and down as I move through the Moiré pattern. In other words, it acts just like a potential that acts on the states at the top of the valence band. So as shown here, the one case of particular interest is tungsten diselenide on top of molybdenum diselenide or molybdenum disulfide. The states at the top of the valence band in that case are in the tungsten. So the molybdenum doesn't play any role other than to provide the modulation pattern, which is easy to understand intuitively. Roughly what it comes from ends up having an energy scale around 60 millielectron volts. The length scale on which this variation takes place is tunable just by twist angle. And if you assume this potential is periodic and takes, smoothly periodic, in other words, you can use the lowest shell of reciprocal lattice vectors for an expansion, then it can be expressed in terms of, in this case, just two parameters. And so you can have a simple phenomenological model with fixed modulation strength, but tunable via twist angle modulation period. And if the spatial scales get big enough, for example, the electrons will nearly get trapped in the potential minima because they have to tunnel through large distances to another minimum, and you get these very narrow bands formed that are, whose physics is more or less described by a Hubbard model. I mentioned before that there's no spin at a given momentum, but spin is locked to momentum, and there are two valleys, two momentum regions of interest. So this actually maps to a Hubbard model, or at least a particle in a periodic potential with a spin degree of freedom, and in the right limits to the Hubbard model. One of the interesting properties here is that, of course, a real system of electrons doesn't just have on-site interactions like in the Hubbard model. It has long-range interactions too, and people have shown in experiment. These experiments, there are 3 first papers looking at strong correlation physics in this system came out on the archive last fall, and one of the interesting things that they see is Wigner crystal states, which are broken translational symmetry states, are very common and presumably obscured by disorder in real in crystals that are often described by Hubbard model. These are Wigner crystal states, let's say, where every 3rd site is occupied, for example. And an interesting thing about these TMD systems is that you can probe them optically. And this is an optical, for example, an optical dichroism measurement from the paper of Tang et al. At Cornell, which is basically measuring the magnetic susceptibility of electrons in this lattice as a function of temperature. All of these temperatures are above where the ordering temperature is in this system, and as a function of band filling. So there are interesting things you can do. Let me just mention very quickly that that's not all you can do, even though you can't do everything. It turns out that there are other other TMDs. This is work that I've been doing recently with an exchange student Mattia Angeli from CISA. And in certain TMDs, the highest top of the valence band in bilayers is near the gamma point. And it turns out the emergent symmetry there is of a honeycomb lattice, that of a honeycomb lattice, not a triangular lattice. So we can have 2D triangular lattice, Hubbard model-like systems, and honeycomb lattice systems that have not been studied experimentally yet. And we also think that bilayer systems will have interesting properties. So my remaining time, I'm going to talk about twisted bilayer graphene. I think I have a little less, maybe 15 minutes or so. And so graphene is, first of all, bilayer. We're interested in bilayer graphene moirés. Many of you probably know that graphene is, basically at low energies consists of carbon pi orbitals on the honeycomb lattice in blue in this more detailed band structure plot. There are 2 bands in a honeycomb lattice because a honeycomb lattice is a non-Bravais lattice with 2 atoms per unit cell. So this additional degree of freedom that forms the conduction and valence bands of graphene can be understood as the sublattice degree of freedom of a single graphene layer. So there are 2 states in this low energy range of interesting in a single layer. And if we have a bilayer, then we have 4 bands. And that means that our model of twisted bilayer graphene has to be a model with a periodic Hamiltonian involving 4 component spinors. And that periodic model, following the point of view that I just explained to you for the TMD case, and which we applied some time ago to graphene bilayers, and this work with Rafi Bistritzer, and has been improved in more recent work. Each layer, like isolated graphene, has a Dirac cone that I just showed you. And the main way in which the 2 layers influence each other is by tunneling between these layers. But the tunneling between layers is sublattice dependent. There are two sublattices on each side. So tunneling Hamiltonian is a 2x2 matrix of complex numbers that describe these various tunneling amplitudes. And in this theory, those tunneling amplitudes are periodic functions of position with the periodicity of the Moiré pattern and with the expected symmetries at the high symmetry stacking points. So for example, at AA points, there's no B sublattice to A sublattice tunneling, which is a complex number indicated by blue arrows here for amplitude and phase. So that simple model applied to twisted bilayer graphene gave this very surprising property, which we didn't understand, so we call magic. And that is that at certain twist angles, the bands became, the low energy bands, at this point in this figure, became extremely flat. Those low energy bands are, they're not flat because of isolation of states in atomic-like, isolation of electrons in atomic-like states, as in the TMD case. Here, it's some kind of interference effect between the hopping within the layers modeled by Dirac-Cohn and K-dependent, and the position-dependent hopping between layers. And I won't have time to talk about the current understanding of why there are magic angles at certain discrete angles, but it's certainly clear that the physical properties of these Moiré band systems are extremely interesting, with superconducting domes all over the place. This is showing filling up the bands. It turns out there is a flat valence band and a flat conduction band. And each of those bands has a valley degeneracy I was referring to before, plus spin degeneracy. So there are actually 8 flat bands. Most of the time there are insulating states at integer fillings of these 8 flat bands. And superconductivity is common all over the place. And let me just start from here. So I'm going to talk in my remaining time, and Matthias, just give me a 2-minute warning.
Yes.
One of the very interesting things that's been observed in these artificial 2-dimensional crystals is the quantum anomalous Hall effect. That means the quantum Hall effect without a magnetic field. And the quantum Hall effect, the fact that the quantum Hall effect could occur without a magnetic field is, maybe was already partly clear from the work of David Thallis, but explicitly shown by Duncan Haldane in a toy model. In a paper published in 1988. This cartoon at top is from Haldane's paper. The quantum anomalous Hall effect has now been observed experimentally in 2 different types of systems. One is magnetically doped topological insulators, which like graphene have Dirac cones, but the Dirac cones here in that case are localized in real space on the top and bottom of a magnetized topological insulator. Whereas in graphene, there are, in twisted bilayer graphene, there is a remnant of the Dirac cones in each of these layers, in each of the 2 layers in each valley. And the physical mechanism that's responsible for the formation of the quantum anomalous Hall state in graphene, twisted graphene bilayers is actually spontaneous valley polarization, plunking of all of the states, an energetic preference for putting more electrons in one region of momentum space than another. Interestingly, this was actually a theory of superconductivity, maybe lost in the mists of time, but there are a few papers written by Heisenberg in London, who contributed very much to physics, of course, in the 40s, which really said that this should occur. As far as I know, magic angle twisted bilayer graphene is the first actual example of momentum space condensation. And they had the notion, they recognized that such a state would break time reversal. They thought it might carry a current, a supercurrent, and be responsible for superconductivity. Instead, what it does is it carries an orbital current. And it's important that the magnetism of twisted bilayer graphene does not involve spin. So this orbital current, which produces orbital magnetism, is the only kind of magnetism that's around. And I don't have time to go through this in detail, but let me just say that many of you are familiar with the Schrader formula in the theory of the quantum Hall effect. Schrader formula says that if you have a system that has a quantum Hall effect, the density of states that are occupied below a gap should depend on magnetic field. And simple quantum Hall effect, this is just Landau level degeneracy, but Chern insulator, it's also true that the density of states depends on magnetic field. And just by thermodynamic identity, that also means that the orbital magnetization in a gap of a quantum anomalous Hall system, the orbital magnetization depends on chemical potential. And orbital magnetization is the dominant magnetization in these Chern insulators. And so the magnetization changes in a given magnetic state by a lot, just by doping the system slightly N-type or slightly P-type. You can calculate that explicitly. I don't have time to go through this, but this is I'm showing you now a very interesting recent preprint from Pulsion et al., the group of Andrea Young at UCSB, which is measuring the anomalous Hall effect in a quantum anomalous magic angle twisted bilayer graphene system. Measuring it here, it's showing it as a function of density, but this is just a gate voltage. So this is electrical control along this axis. The anomalous Hall effect is basically proportional to valley polarization, or its sign depends on valley polarization. So this is showing you that you can change the sense of valley polarization very abruptly just by doping the system N-type or P-type. And so that's a very unusual property. And
2 minutes, Allan.
2 minutes, okay, 2 minutes for superconductivity. Superconductivity is, of course, perhaps the most interesting and surprising property of these artificial two-dimensional crystals. We don't really know what's responsible for the superconductivity yet, but perhaps we're zeroing in on it. One idea is that, it's mediated by phonons, either optical phonons, and, optical phonons give something in the right ballpark, but as usual with superconductivity, you have to deal with the repulsive Coulomb interaction between the electrons, which we don't know how to do rigorously, certainly not in this case. Acoustic phonons are also thought to be a possible mechanism. And in connection with acoustic phonons, one of the very, very interesting properties of magic angle twisted bilayer graphene is just near the magic angle, there's a huge linear in T, temperature-dependent resistivity, which of course violates Fermi liquid ansatz and certainly indicates, abundant, very abundant, low temperature inelastic scatterers. And one of the ideas is that this could be due to phonons if you have small Fermi surfaces, because only phonons with small wave vector that could scatter you between electronic states on the same Fermi surface. But it's important to realize that the states in a Moiré crystal are not plane waves. They're periodic block functions. And when you take that into account, then you find that you do not get linear in T resistivity from this mechanism. So acoustic phonons can't be responsible for this huge, very prominent linear in T resistivity, and they're not, so it has to be something else. One possibility for something else is these excitonic collective modes we've discovered recently. Maybe they're responsible for the linear in T resistivity. Maybe they're responsible for superconductivity. And maybe somebody will ask me a question about this. So I will stop right here. Thank you very much.
All right, thank you very much, Allan, for this very interesting talk. So let me pass over to Johannes for the moderation of the Q&A.
Yes, thank you very much. And just a general for the audience, if you please use the Mentimeter to pose your questions. And indeed, there's already one question there, and let me just read it out to all of you. So it says, what would be a minimal Hubbard model type description for the twisted bilayer graphene without, I guess, the complication of all the other higher bands?
Yeah, so this is a very interesting part of twisted bilayer physics that I had to skip over. Because the bands really should be thought, because there are two layers and each of these two layers has a Dirac cone. You may remember this famous theorem in lattice gauge theory that Dirac cones appear in pairs with opposite vorticity. Here there's a pair with the same vorticity within each valley. And that means there's topological, these bands actually have topological properties, and there's a topological obstruction, I would say, to making useful Hubbard-like models. There is some work trying to derive Hubbard-like models. You have to add auxiliary bands to cure this topological obstruction problem. I think it's not the way to go, but if you did, you probably need at least 5 or maybe 8 bands per valley per spin. So you would need at least a 30 band, say, Hubbard model, which is starting to sound unattractive. And therefore, we seem to be stuck with a continuum model description.
Okay, other questions? So I see no other immediate question, but I may ask one. Namely, so far you always assume that you have a perfect twist, but wouldn't you also expect in reality that there is an inhomogeneity of the twist on the lattice level that would have strong influence also?
Yeah, so that's a great question. There are two types of corrections to the model of rigidly twisted layers. One correction is just relaxation from this rigidly twisted structure, which when coarse grain gives you some also periodic distortion of the underlying lattice. And that periodic distortion, most of the time doesn't do much of interest because it just changes the periodic Hamiltonian slightly. So I mentioned that we often describe the Moiré pattern in terms of a small number of parameters. And so those, the values that those parameters have certainly should reflect the this distortion or strains that appear that due to relaxation of the lattice. But there is another type of thing that especially an issue for twisted bilayer graphene, where people can make perfect moiré patterns, but only by following a recipe which ignores long length scale variations in the local twist angle, which seems to be the most prominent type of disorder in at least twisted graphene moirés. And so people have gotten better at getting rid of that disorder, but one of the consequences is, basically it comes from little bubbles that you form when you lay one layer on top of each other. And in order to, when you iron out those bubbles, as Dima Yefetov in Barcelona describes what he does, and that's the person who's developed the best recipes for doing this, you end up with a sample that has a twist angle that's different from the one you aimed at. And the fact that you can't just have your graduate students create a bunch of samples at all twist angles spaced by 0.05 or 0.005 from 1 to 1.2 has been an obstacle to getting really good experimental results on some of the systematics in the twisted bilayer graphene case. Okay, thank you very much. So I think in the interest of time, we will actually move the discussion to the round table. So for those of you who have more questions, please join us at the round table discussion and post these questions there. Yes, and thank you very much again. For this. Okay, thanks everyone.
All right, thanks a lot. Also, Tanya.